All right, we'll continue now. If you can write this down, next lesson. Can you see? Yep. Jeffrey, you have this? Hello? Did you write this down? Come on, we'll start the next lesson now. Yep, okay. All right, so what we're looking at now, cantilevers and further support. Yeah, a couple small things. So the first thing is, what the heck is a cantilever? So I have 3 pictures here of 3 types of cantilevers. The first one is called a simple cantilever. You might see these. You might see these, but really you don't see them because they're not very useful. There's no support under it. It's too weak. Yeah. Now this one is much more common, isn't it? This is called a braced cantilever. Where might you see a braced cantilever? No, somewhere in the home, or something like a braced cantilever. Yeah, maybe a table shelf. You fold the table out and you put the support under it, or something like this. The last one's called the braced. Oh, and this is called the strut. The last one's called the braced cantilever, and this is called the stay. It's like a string. Where might you see a braced cantilever? Where? Say again? What's this? Oh! Yes, but I was thinking more about your home. Unless you have a bridge in your home, do you? Maybe to get into the home, I don't know. A bridge, yeah, or a door like this. But where might you see it in your home? Chair? What type of chair? You have a chair in your home that you pull down and there's a string on it. No, so that's what I'm asking.
The oven door.
Does your oven have a string? Well, maybe. No, I was just thinking like...
Does it have to be a string?
It usually is a string. It doesn't have to be. It usually is. A desk, a writing desk. You open the drawer down for writing desk. You don't have this? Would have a string though? Maybe. Look, okay, another example is when you're outside a shop, maybe there's a sign hanging from the shop. Yeah, or something like that. Okay, these are cantilevers. There's actually a cantilever outside the office downstairs. When you're going down the stairs, you look out, you'll see a cantilever somewhere. I'll let you discover it for yourself. So, the definition now of a cantilever, it's a little bit technical. I'll need to explain it word by word. So, a cantilever is a rigid structural element. Okay, so the first word, rigid. What is the meaning of the word rigid? Strong. Yeah, strong is fine. What else? Stable is fine, yeah. Rugged, yeah. You all understand that it's something solid that you can't... Yeah, firm. You can't change the shape. Structural. What does structural mean here? Yeah, it's defined in shape. Used in a building, usually. An element just means an item. Okay? Such as a beam or a plate. So, a beam, I don't see any in this room really. Well, here. You see this here? These pieces of wood. You could call, oh, actually I can't take it off. Sorry. This is like a beam, or a beam or a plate. So for a cantilever, it might be attached to the wall like this. Okay. So this is kind of like a cantilever, but it's not really because it's not stuck to the wall.
What's inside?
Oh no, I'll let you discover for yourself.
It's too much private.
Nothing exciting. That's a beam or a plate. Next, anchored. So the reason I said that's not a cantilever because it's not anchored. What does the word anchored mean? Attached, but in a very solid, strong way. So for example, even better. The projector. You see on the top of the wall, on the ceiling, it has 4 screws. They are very strongly attached to the ceiling, right? So we can describe them as being anchored. Really strong hold. Okay? I maybe could hang out that and it wouldn't fall. But I won't try. Huh? Yeah, and I would suspect that those screws are going into a beam on the other side of the ceiling. No, I know this because I did this in my home. I was attaching something to the ceiling, and you have to go up to the attic and make sure when the screws go up through the ceiling that they actually go into a wooden beam and not just the ceiling. Otherwise, if you pull on it, you'll pull a big hole in the ceiling. So I hope that they're attached to a wooden beam on the other side that maybe is running across the ceiling. That is true. But I won't risk it. Okay. Usually to a vertical support, so usually to a wall, from which it's protruding. What does the word protruding mean? Yeah, what's it mean, yeah? Yeah, sticking out. Protruding means sticking out. Now, what I would like you to do... What's wrong? Is that okay? This is, I know, it's a very difficult definition. Lots of difficult words in it. Oh, okay. What I need you to do is to draw this and write the definition down. Yeah? You have it? Oh, okay. We'll just give it a minute for other people. Now, don't worry. In the exam, I don't think they'll ask you for this definition. But you should know the names of those diagrams. Because maybe in the exam they would give you a question with no picture. Do you know what I mean? They might say blah 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 is a simple cantilever or blah 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 braced cantilever. You need to know which picture you're looking at. Okay? Is cantilever a new word? Yeah? No? Continue? No? Yeah? Okay, come on. Come on, he's ready. What part are you at, Marwan?
Just simple names.
Oh.
I'm thinking.
Are we just waiting for Marwan?
I'm finished.
And now we're just waiting for Bello?
Yes. I'm done.
Oh, okay. What? You need to have words with him afterwards. Yeah. You need to have words with him afterwards. You'll say, "Dear Mr. Neal, I have to report to you some troublesome students in the class." Especially, yes. Right, continuing. So, let's have a look at the first example. I'll draw the picture. A 40 centimetre beam cantilever of mass 10 kilograms has a 2 kilogram mass placed on its end. So let me draw the picture here for you. Here's the wall. And how long did I say the cantilever was? 40 centimetres. 40 centimetre cantilever. Yeah? It has a mass of 10 kilograms. So right in the centre here, there's a weight of 10 G. 10 kilogram mass. Also, there's 2 kilograms placed on its end. So here it is having a 2G force. Okay? It is a braced cantilever. What does that mean? Yeah, which diagram is a braced one? That's the second one. Oh, sorry. It's a braced cantilever supported by a stay. So, whoops, which one is it now? The third one, yeah. The stay is attached 30 centimetres up the wall, and the other end is attached to the end of the cantilever. So, it's like this, here to here. Okay, and this distance here is 30 centimetres. Now, remember, this distance from here to here is 40 centimetres. So, you can actually know the length of the stay. Try again. 50 centimetres. You got too excited. You were thinking of 3, 4, 5. Yeah, 50 centimetres. Yeah. First, oh, and also, I need to draw here the tension. I'll call it, actually I'll stick with blue for force. Tension T. Now, before we start, we should write down what is the angle here. We can actually know this angle, can't we? What would we type in on the calculator to get the angle? Tan inverse 30 over 40, which gives us what? What is it? Yeah, so 8, 7 then. Yeah? Now, what I'll do next, I'm trying to get the tension in the stay. Well, what do you think I should do next? Resolve it, yeah. We'll have a force this way, and we'll have a force this way. Now, my picture's getting a little bit crowded, so what I'll do is I'll just draw them over here, okay? Yeah? How big is this one? T cos 36.87. I think cos 36.87 is 0.8? Yeah, 0.8. So this would be 4/5 T. And then this one here, what's that? That's T sine, and that will work out to be 0.6, which will be 3/5 T. Okay? Right, what's the next step here? What's the next step? Yeah. There's actually something I haven't drawn on the picture. There is some kind of force here. a reaction force. Now, I don't want to deal with that just yet, so I'll use a little trick here. I'll make this point here the turn-in point. So if I look at the four forces, 1, 2, 3, 4. Only 3 of them matter. Which one do I not care about? The one pointing to the left. Why not? Doesn't turn it. Yeah? Okay. This force, will it make it move clockwise or anti-clockwise compared to this turning point? Were you looking at the clock to figure this out? No, it looked like it. This one here, anti-clockwise. This one here, clockwise. And this one here, clockwise. Yeah? Yeah? So, this distance here, what's the distance? 0.2 times 10g plus 0.4 times 2g. Good. That should equal 0.4 times 2. Can you figure out the t from this? Of course you can. I'll give you a minute. Tell me the t here. You got the t, Ming? What's the t? Oh yeah, well, do you know what the t is? Did you calculate? What's it, Jason? What did you get, Marvon? 24. Hang on. Did you get an answer for T? Oh, come on, give me an answer for T. What did you get? Oh, Jason, what did you do? 115 newtons. Yeah? Well, that's what everyone's saying. Yeah? Except for Jason. Wouldn't it be funny if Jason was the only one right and you all screwed it up? The chance would be 50-50 maybe. Right. Oh, in the question I said there was a 2 kilogram weight at the end of the support. Some object, yeah. Can I continue? Yeah. B. How much horizontal reaction is provided at the hinge? So actually, there's a reaction here that I haven't drawn. And I wonder if you can tell me, is the reaction horizontally here to the left or to the right? Why? Yeah, true. Why would it move to the left? Yeah, you got it. So we'll call this force here, I'll just give it a name, I'll just call it X. I mean, it's obvious. Think about it. If you're pushing into the wall, then the wall has to be pushing back out. What will this X equal? Very good. 4 over 5t, which will equal what? What is it? 92? 92 newtons. Okay, C. I'm going to ask, what is the vertical reaction? So, again, Will it be up or will it be down? No. Why? Because it's not down. Yeah, and your teacher said it's not down. Yeah, but why is it up? Oh. Right, so think about this, guys. If you hang something on the wall, it will naturally want to fall up or fall down. But it doesn't fall down, does it? So there must be some support from the wall, like at the hinge. You know, like if this was attached to the wall, it's not falling down. Because maybe the screw here is providing an upward support. Right? Like, look, actually, there's a simple cantilever up there. Do you see the camera on the wall? Up there. Okay? That is not falling down on David. No matter how much we might wish it would, it's not falling down on David. Why not? Because the screws on the wall are providing an upward force to cancel the weight. Is there anything else that's providing an upward force in that diagram? Is there any string? No. Any support underneath, like a brace? No. It's only the screws on the wall are providing an upward force. So, attached here, there is an upward force of Y. What would that equal? What would that equal? It will equal, look carefully, look, it will equal 3/5, it will equal, but you know what, I'll write it like this and be easier. Y plus 3/5 t. What should that equal? Yeah, which is what? 12g. Right? How many upward forces are there in this diagram? There's two. There's the reaction at the wall provided by the screw, perhaps, and there's also an upward tension force. These two together must equal the total downward weight of 12g. So, do we know this? Yep. Can we know this? Yep. So now we can know y. So tell me the y. .72 newtons. Okay. We'll just 7.2. Right. D. What is the magnitude of the reaction? So if you combine these two reaction forces, you'll get a total reaction force in this direction, which I'll call or. Yes? Now what's interesting is, at the start of the question, you might not have guessed that that was the reaction at the hinge. I want you to calculate the or here. How would you calculate that? Pythagoras, good. So calculate that, please. 103? Yeah, 103 newtons. Yeah? Okay. Lastly, what is the direction here? So lastly, I want this angle. How do I get this angle? Tan inverse of? Tan inverse of what? Yeah, tan inverse of y over x. What will that equal? 27.9 degrees. Now, this isn't a super straightforward question, but I mean, I don't feel like any one step was too difficult. It's just that there were many steps here. Yeah. I want you to write this down carefully. There is another way to do this that we'll see in the next lesson, but for today, just write this down carefully. And let me just. Yeah. We have one more example to do that's like this one, so write this down. Can you see it all okay? There's everything on the diagram. There we go. Diagram's a bit crowded now that we kept adding to it. Nikita, come back, wait, come back. Go around the long way.
Oh, yeah.
Yeah, yeah, that too. The physics students will be distracted.
Oh, yeah.
He was being a bit cheeky, trying to sneak through the short way here with a physics class going on. You got that? You got that, guys? Yeah? What does he want? Go away. Go away. Right. Okay. Continue? Yeah. So, next one. A 13 kilogram ladder of length 13 meters is up against a wall, and its foot is 5 meters from the foot of the wall. The wall is smooth and the ground is rough. What is the angle of the reaction force at the foot of the ladder? So I'll just give you one moment to draw the picture. I just want to see if you can draw the picture. Just try to draw this story. So this is no, I won't let you try. See if you can draw it. Right. Did you draw something? Okay. So you have the ladder here like this. Yeah? And this distance here is 5 meters. And this distance here? 13 meters. And this distance there, therefore, is 12 meters from our buddy Pythagoras. Now, let's add in the forces. So, what force do we have here? Yeah, well, how much? 13G. Now, you have two forces here. There's one force provided by the ground, which I'll call Y, but then there's also a friction force that stops the ladder from sliding. Which direction will this friction force be? Left or right? Left. Because the ladder wants to move right. It does not. Because the friction is left. And here there is a reaction force. But I say that the wall is smooth. So there is a force this way, but there is no force this way. Because think about it. Imagine that this wall was made of ice. If I put my hand against it here like this, it will slip down. There's no upward reaction here. The only reaction is horizontally if the wall is smooth. Okay? What do I need to calculate here? I want to calculate the angle of the reaction force at the foot of the ladder. In other words, I want to calculate this angle here. So, if I want, let me draw this again, X, Y, S, I want this angle here. So if I want this angle, what will I need to know? I'll need to know X and Y. Let's begin. I think the easiest one to get first is which? Yeah. Y should equal 13G. So Y equals... No, it's 13G. Newtons. Okay, fine. Now, we just need to get the X. This is a little bit harder because if we say X equals or, well, that's not helpful because do we know the or? No. So, here we said up equals down, left equals right is no help. So what's the last thing we can use? Clockwise and anti-clockwise. Now, we can put the turning point anywhere, but there's a really smart place to put it in this picture. Where? Well, where would be a stupid place to put it? No, there's even a stupider place. Now, the middle is not stupid, but there's a really stupid place to put it. At the bottom. Why would it be stupid to put the turning point here? Why? You're looking for X. And what would happen if you put it here? The X would be gone. Why would it be a bad idea to put it here? What letters would be in your equation? You would have X, fine. You'd have Y, fine. And you'd have OR. Oh, well, that's a problem because we don't know OR, do we? So there's only one smart place to put it. Here. This will cancel out the OR, won't it? The equation will contain X and Y, won't it? Do we know Y? So we can get X. Now, let's calculate this. So how many forces do I need to look at? No. 3. 3. Yeah? So, let's look at this first force. Is it a clockwise or is it an anti-clockwise? This one here. Now say it with confidence. There we go. Okay. This one here, the x, is also clockwise. And the y, anti-clockwise. Okay. Let's calculate the clockwise. It'll be 13g times the distance. Now, you can look at it like this. Here is the force, and the perpendicular distance is this distance. What is that distance? 2.5. Very good, 2.5. That should equal... oh, sorry, is that clockwise? Yeah, plus there's another clockwise. The x here. X, and then if I draw it nice and big here... No. What's the distance to this force?
12.
Very good. 12. Remember, it's the perpendicular distance, the shortest distance. And lastly, what's the last one? Y. And what's the distance to the y force? Let me draw it in nice and big. There's the y force. What's the distance to it? It's 5, isn't it? Here it is here. But do we know the y? Yeah. It's 127.5 times 5. So, can you get the x? Yes. And now that you know the x, can you get the theta here? Yes. So I need you to get me both, please. Not easy. Well, it's funny. It's not easy, but I've not written much. Have I? I draw much, but not written much. This, I think, is part of the problem in the exam. Too much imagination and too much drawing. Students don't like to do this, it looks like. So what's the x here? $26.5. Okay. And then what is the theta? It would be tan inverse 127.5 over 26. Yeah. Do you remember when I gave you the definition of turning force? I said there's actually two ways to calculate it. You could resolve the vector and use that, or you can use the original force but the perpendicular distance to it. So you've only remembered the first way because that's the only way we've used up until this example. But now in this example we use the other way to calculate turning force, which is the force times the perpendicular distance. Previously we've been using the distance times the x component of the force, or the y component of the force. Now look, this is exactly the reason why I record the lessons. So that if you found this confusing the first time, when you watch it the second time, you will find it less confusing. You should know this whenever you've revised maths or physics before. The first time you learned something, difficult. 1 month later, when you look at it again, you might start to ask yourself, why did I find it difficult the first time I did it? Right? You know, Ming? No? Not true? Would anyone agree that it is true? Or maybe for others? Yeah? Okay, so look. I said to you that there are two difficult topics in semester one. They are mechanics, projectiles and turning forces. Maybe you're starting to see why I say the turning forces are difficult. Okay? Now, the good news for you is that the previous lesson is more common in the exam than this one. Okay, because I think the last lesson is really on every exam, whereas this one is only on some exams. Okay? So, what we can do with the last about 10 minutes is you can either continue with the homework from the first lesson, or I think this is a better idea, if you try to do at least one of these now from the workbook. Okay? So get started on your homework now for, what have we got? 10 minutes? Yeah, 10 minutes. Can I close this? Not yet? Yeah.
So how did you determine the clockwise and anti-clockwise in this situation since there's no...
Same as before, Bello. Imagine that the ladder is a clock hand. What hour is it pointing at in the picture?
One side with the...
Take this point here, Bello, take this point here as the center of the clock, and take this as the clock hand, the hour hand. What hour is it pointing at, roughly?
5.
About 5 o'clock, isn't it? Okay. So, if you hang a weight here at the center, what are you going to make the clock hand do? Move forward in time or backwards? Forward, so clockwise. If you pull it to the left here at 5 o'clock, what will you do? Run it forwards or backwards? Forward, clockwise again. But what if you use your finger to push it up? Go anti-clockwise. It's the same technique as in the previous lesson. What's wrong, Ming? Are you sure? Okay. Close this.